All right, so our next unit is projectiles, and this unit is a culmination of really everything we've done up to now. It has velocity, it has acceleration in it, it has free fall in it, it has kinematics in it, and it also has vectors in it. So I don't know if that's good news or bad news for you, but it is a culmination of all the things that we've done up to now. And then after this one, we kind of shift gears and move into forces, which is similar math, but not everything that we've done from the beginning. So let's define a projectile first. We know that we're in the vacuum that we can breathe, and that is constant for our entire class this year. The object moving through the vacuum we can breathe in two directions. Okay. So that's the idea with projectiles, is not only is the object moving in one direction, but it's moving in a second direction. And we can break those down into two different directions. We say that one is the y direction, and that's the vertical direction, and the other is the x direction, and that's the horizontal direction. And you can have two types of projectiles. You can have horizontal and you can have angled. The horizontal projectiles are a little more straightforward, and that's what we'll start with. And the angled ones can throw you for a loop a little bit, but they're not too bad, but they are a little harder than horizontal projectiles. So we'll start off with horizontal projectiles here. And we have a cannon just sitting on a cliff, and it's shooting a cannonball out. And we can see that the cannonball is moving forward, but it also is falling as time goes by. And that's something we'll key on, is that time value later on. So let's take the vertical component first. Over here on the left, I have a graph of an object in free fall. And we notice that as it's falling, it covers more and more distance, and that's something that we have talked about before in free fall. We know that as it's falling, it's getting faster, it's speeding up at 9.81 meters per second squared. And because it's speeding up every second, it's going to cover more ground every second. So we know that it's getting more and it's getting faster and faster as it falls. We know it's pulled downward by the force of gravity, and we know the value for the acceleration is negative 9.81 meters per second squared. And the distance and velocity increase on the way down. And for this type of, this part of the projectile motion, we will use our kinematic formulas, because in projectile motion, if you're talking about the vertical component, you're talking about an object that's accelerating at a constant rate. So you will need to use your kinematic formulas. Remember, they are the ones that we would use in free fall, because we're talking about acceleration along the y-axis, not really horizontal acceleration. So yeah, you got to use kinematics for this one. All right, so the horizontal component, the forward component, is kind of like if you think of a hockey puck. If it's sliding along frictionless ice. Now, of course, frictionless, we're not dealing with real world here. We're dealing with perfect world scenarios. So we're saying that there's nothing to slow the puck down. So because of that, it's going to stay at a constant velocity. It's not going to speed up. It's not going to slow down. It's just going to continue to move at the same velocity the entire time the projectile is in motion. So there's no acceleration, which means that it would cover equal distance every second, unlike the vertical component, which of course is accelerating at 9.81 meters per second squared. And if you look at a picture here of the ball moving forward, you'll notice that each ball is the same distance away from the previous one, identical. From here to here, from here to here, from here to here, from here to here, here to here, here to here. Same distance covered every second. So when we're talking about the horizontal component, because there's no acceleration, we can't use any kinematic equations. And if we can't use any kinematic equations, we have to default to our velocity formula, which looks kind of odd the way it's written here. Let me rewrite it. So it's the x velocity is equal to the change in position final minus the change in position initial over time. Of course, we know that this is simply our delta x. And we're using x here because it's horizontal, so it's moving along the x-axis. And again, no kinematics for this x direction. So if we combine those two pictures, the horizontal component would be the green, and the blue would be the vertical component. And we notice when we combine these together, we see these red balls. And if you look closely, the distance between horizontally between each one of these is identical to the distance of each one of the green balls. And if you look at it vertically, you'll notice that the distance that it falls every second gets greater and greater. And because it gets greater and greater, we know it's accelerating. And we can see that with the blue over here. So even though the horizontal and the vertical components of a projectile, even though mathematically we solve them different ways, there is one variable that they do share, and that's time. They do share the time. And that's very important because on a lot of problems that you'll do, you'll have to find something along, say, the vertical component, and the time might be missing. But if you know the time for the horizontal component, they are the same value. And if you think about it, it makes sense. If an object is thrown forward, it's moving forward for the same amount of time it's falling. So the vertical component is falling, it's accelerating. At the same amount of time, the horizontal component is moving at a constant velocity. They share time. So if an object is moving for 3 seconds forward, it's also falling for 3 seconds. Or if an object is falling for 10 seconds, it's also moving forward for 10 seconds. So time is something that both the x and the y share. And that's very important to know. So this is a very famous physics thought experiment that first-year physics students always tend to have trouble with. And it's this idea that if you have a bullet in a gun and you fire that bullet, we know that it goes out, and as it goes out, it starts to fall immediately the second it leaves the chamber. And if you have a second bullet that you just drop from the same height that the bullet was fired, and the question always is, which bullet will hit the ground first? Well, stop and think about it. And if you think about it and you don't use proper physics, you might think, oh, the bullet that's moving forward has to stay in the air longer because it's got that forward speed. Well, that's not the idea. The idea is that gravity doesn't take a holiday on an object moving forward. It treats the object moving forward the same way it treats the object that's just falling. So the answer is a trick question, or the answer is tricky. And that's the idea that both objects hit the ground at the same time. So if you drop the bullet at the same time the bullet is shot forward, now again, this has to be horizontal here. I'm not saying that you shoot the bullet up in the air and it goes up and then back down. I'm saying if you shoot it horizontally out from the bullets, the chamber of the gun, that bullet starts to fall at the same rate that a bullet that's just dropped falls. The horizontal component has nothing to do with the rate at which it falls downward. So that's the idea, that both objects will hit the ground at the same time. So there's a few variables that are new to what we have been talking about up until now. The first one would be Vx, and that's simply the velocity along the x-axis. So Vx is the forward momentum, forward velocity of the object, and the idea, of course, is that the Vx never changes throughout the path. So if I was going to try and draw the Vx vector for the entire motion of the ball, I would try and draw all of those arrows the same size, because what we're trying to enforce is we're trying to say that that Vx never changes. Vy, on the other hand, that's going to end up increasing. Over time, the Vy velocity is going to get greater and greater. So I would draw my Vx vectors, my Vy vectors farther or longer over time, just to emphasize that the Vy is increasing because the object is accelerating in a downward motion. The height would be delta y, how far the object's falling. And then delta x would be the range. And the range is an important part of projectiles. It's the horizontal distance that an object goes when it is launched. Whether that's up or down. You know, if you have an object here and it goes up, 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 and then goes down, 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 and lands here, the range is how far it was from where it started to where it landed. Now, we just got done with vectors, and we talked about how if you were given an x component or a y component and you wanted to find the hypotenuse, you could. Or if you were given the hypotenuse, which we call the resultant, you could find the x and y components. Well, with vectors, or with projectiles, we're actually going to make use of that idea. The question here is asking you to find to find v, the resultant, and it gives you Vx and it gives you Vy. Now remember, Vy could also be drawn over here, because we know in a parallelogram that the opposite sides are going to be the same. So I could write over here that Vy equals 4 meters per second. And that might be easier for you to understand because it looks more like a right triangle. But you can use the parallelogram method for the same thing. So how do we go about finding the velocity overall? It's moving forward at a certain rate, it's moving down at a certain rate. How do we find the overall velocity? Well, that's what we're going to do is what we would do if we knew two legs of a triangle and we were trying to find the hypotenuse, we would use the Pythagorean theorem. And we know the Pythagorean theorem is a squared plus b squared equals c squared. And c is our hypotenuse. So if I was going to rearrange, I would just square root it to get rid of squared on the c. And then a, doesn't matter which one I call a or b, I'm just going to call the, well, you would write it like that, and then you would start plugging in your numbers. I'm going to call a squared, let's just call a the Vy. So we're going to call that 4 meters per second squared plus 3 meters per second squared. And when you do that, you end up with 25 square root, and of course the square root of 25 is 5, and that would be meters per second. So that would be the value, which of course we see is revealed over here. That would be the value of just the speed, the overall speed of the projectile, but we don't know the direction, and that means we need to find the angle. Now I could use inverse tangent, I could use inverse sine, but I'm going to use inverse cosine. It really, like I said, doesn't make a difference. You may want to use tangent inverse because you are given these two values here, but I'm pretty sure the 5 meters per second. So I'm going to use inverse cosine. So cosine of the angle equals the adjacent side over the hypotenuse. So if I take the inverse cosine of both sides, the adjacent side is going to be here. This is my adjacent side, so it's going to be 3. And the opposite side is going to be the 4 meters per second, so 4 right there. oh, sorry, the hypotenuse, check that. That's if we were doing tangent, and it would be flipped actually. So yes, the hypotenuse, excuse me, is 5. And so the cosine of 3, the inverse cosine of 3 over 5 is 53.1. Now how are we going to describe that in terms of cardinal directions? Well, it didn't really give us any cardinal directions, but if I had said that this was east and this was south, you could say that this was 53.1 degrees south of east. You could say 53.1 degrees below the horizontal. That would be acceptable as well, and probably be more appropriate since this problem doesn't really give us any cardinal directions. So your final answer would be 5 meters per second at 53.1 degrees south of east would be your answer for that one. So our first official projectile example says, while moving in his car at 10 miles per hour, or 4.47 meters per second, Mr. Martin drops a ball from a height of 0.7 meters above the top of a bucket. How far in front of the bucket should he drop the ball in such a way that it lands in the bucket? And then B says, what is the overall velocity of the ball as it entered the bucket? All right, so we have this ball, and what we're going to do is we're going to try and see if we can, as we're driving to the right, let's just say it's to the right or east, we're going to see if we can drop it just so that it lands right in the bucket as the car is moving forward. So obviously I can't let go of it here, because if I do that, it's going to land over here. So what we're trying to do is figure out how far away, in other words, the range. What's the range going to be? When do I need to let it go so that it travels, whatever that range is, to fall right into the bucket? Anytime you're doing a projectile motion problem, if you remember when we did projectile motions, one of the things that we talked about, or excuse me, vectors, is we talked about doing an X and Y t-table. But in this problem, in projectile motion problems, it's a little different, because in the vector unit, we put the X and the Y components together. Here we're going to put the X variables and the Y variables together. So let's talk about what we know about this object as it's moving through the air towards the bucket. Let's take the X side first. So what do we know about this ball moving horizontally? Do we know its forward velocity? Do we know Vx? Well, think about it. If the car is moving at 4.47 meters per second, then everything in the car is also moving at 4.47 meters per second. So we do know that that ball is moving at 4.47 meters per second. Do we know anything else about the forward component? Do we know how far, the range? Well, we don't know that. That's what A is asking you for. Do we know how long the ball is moving forward? No, we don't know that either. If we could find the time, could we solve for delta x? Well, we know that Vx is equal to the displacement divided by the time. So if I could figure out the time, I could figure out delta x. Well, what do we know about projectiles? What one variable does the forward component, the horizontal, the x component, what is one thing that it shares with the y component, the downward component, or the y-axis component, the vertical and downward component? We know that they share time. Time is common to both. In other words, the ball is going to be moving forward for the same amount of time that it's falling. So is there a way I could find the time that it's falling and use that number for the time that it's moving forward? Well, let's think back to our kinematics. We know that if we know 3 variables, we could solve for the 4th and the 5th. So let's write down what we know about the y direction. Do we know the acceleration rate of the ball? Well, we sure do. 9.81 meters per second squared. Do we know how far the ball is falling towards the bucket? In other words, do we know delta y? We sure do. It is negative 0.7 meters. Now, since I decided that the g was going to be negative, I'm saying down is a negative direction, which means I need to make my delta y negative as well. So that's why it's negative 0.7. Anything else we know? Do we know the initial velocity along the y-axis? Well, I think we do. Was it moving downward initially? No, it was stationary. I had to release it. So we know that VIY is 0. All right, so let's take a look. We know that we have 3 variables. We have 1, 2, 3. Can we solve for time if we know 3 variables? Well, if you remember your kinematics, you should be saying, yes, we can. So t is what we're after. So now I got to think of a formula that I would use to solve for t for an accelerating object. And you go think about the variables that we're dealing with. G, delta y, VIY, and t. What one variable isn't mentioned of the 5 that we're used to dealing with? Well, final velocity. So we need to find a formula that doesn't have final velocity. And if you look at your kinematics, you know that the formula VIY t, t being the change in time, plus 1/2 gt squared is the formula that doesn't have VF in it. Well, what happens to VIYT? Well, VIY is 0. So if that's the case, half this formula disappears. And we end up with 1/2 gt squared equals delta y. And how do I solve for t? Well, I get rid of the 1/2 by multiplying by 2. I get 2 delta y equals gt squared. Then I divide by g, and I get t squared equals 2 delta y over g. And then how do I get rid of the squared? Well, I got to square root both sides. So it's square root of 2 delta y over g. And now I'm ready to plug and chug. So t equals the square root of 2 times delta y, it's negative 0.7 meters, over g, which is negative 9.81 meters per second squared. And I end up with t equals the square root of negative 1.4 over negative 9.81. And that ends up giving me a value of 0.377772 seconds. So that ball is going to be falling for 0.37772 seconds towards the bucket. And since I know this value, and remember, this isn't a value that I was asked to solve for, but I need it to find it. So now I come over here and I realize, hey, now I know this value. And if I know this is 0.37772 seconds, then I know this value is 0.37772 seconds. So what formula did we write earlier? We had this one. Vx equals delta x over t. So let's rearrange that and solve for delta x. Delta x equals Vx times t. Well, Vx was given. It was 4.47 meters per second. T, I just spent 5 minutes looking for t. 0.3777772. I'm not rounding that one. Sig fig wise, you're not supposed to round a number. That's not the answer. You got to drag that full unrounded number into the whatever you're solving for. And I end up with 1.6881 or 1.6886. But that's going to give me a rounded 3 sig answer of 1.69 for our answer. So that is our answer to A. So going back up to our car here, if I wanted this ball to fall into this bucket, I would have to let it go when it was 1.69 meters away from the bucket. And it would go right into the bucket. Okay, so the second part says, what was the overall velocity of the ball as it entered the bucket? Well, remember we have three different motions taking place. We have the Vx, which we already know. We know Vx is 4.47 meters per second. We have the downward velocity, which we call Vy, and we don't know that. And we have the overall velocity, which is what this question is asking for. It's asking to find the overall velocity. And this means we're going to have to jump through a couple of hoops here to help us figure it out. The first thing that we're going to have to do is we're going to have to figure out what this is. And then once we figure out what that value is, and we can use that value with Vx to find V. Well, what is Vy? We got to be more specific, because we have two of them. We have the initial velocity and we have the final velocity. As it entered the bucket, certainly isn't the initial, so it's going to have to be the final. So if we're trying to do the final velocity along the y, that takes us back to our t-chart over here. And when we did the t-chart earlier, we knew 4 now. Remember, we solved for time earlier. So is there a way we could solve for our VFY when we know 4? Well, we have lots of options here, don't we? The safe way to do it would be to not use a formula that has time in it. And the reason that it would be safe is because if our time was wrong, we wouldn't cause our final velocity to be wrong because we wouldn't be using the time. So what formula doesn't have time in it? Well, let's see. VFY squared equals VIY squared plus 2GY. And of course, part of this is going to go away. Our VFY, to get rid of that, we take the square root on both sides. And our VIY squared, we know this is 0. So I'm going to completely ignore that. And I'm going to put just 2GY into my formula. So continuing on, VFY equals the square root of 2GY, so it'll be 2 times negative 9.81 G times negative 0.700. And VFY equals the square root of 13.734. And VFY is 3.7 meters per second. Now you have to be smarter than your calculator here, because we know this is a downward motion. Because it's a downward motion, and we labeled down as negative, we would have to make this a negative answer. So that would be, VFY would be negative 3.7 meters per second. So let's go ahead and erase that answer. and I'll rewrite it again, but I need the space. All right, so our VFY was negative 3.7 meters per second. So again, we know this value is going to be the same as this opposite side. So this is negative 3.71 meters per second, and that's VFY. So if I know one side, and I know a second side, and I want to find the velocity overall, well, this is a Pythagorean theorem problem. So a squared plus b squared equals c squared. And of course, c is the v value, the overall v. I got to do a little bit of rearranging. But let's go ahead and plug in our known values. Vf y squared plus Vx squared equals V overall squared. And now I can do a little bit of rearranging. And when I do that, Vf equals the square root of Vfy squared. What is Vfy? Vfy is negative 3.71. And what is Vx squared? Well, Vx is way up here, 4.47. And when I do that, Vf equals 5.81 meters per second. So that right there is the overall speed of the ball. It's the overall speed, 5.81. But this question asks what's the overall velocity? And the overall velocity has to include a direction. In other words, we have to find the angle as well. So how are we going to find the angle? All right, so finding the angle. We know that the cosine of theta, whatever it is going to be adjacent over hypotenuse. And we know that cosine of theta is the adjacent side. The adjacent side is 4.47. That was the given Vx. And then the hypotenuse would be the answer that we found earlier, 5.81 meters per second. That was the overall speed. And of course, if we want to find the angle, we got to do the inverse cosine of both sides. So take the inverse cosine of both sides. By the way, we don't have to use inverse cosine. You could use inverse tangent. You can use inverse sine. Either way is fine. And when we do that, we end up with 39.7 degrees. And we didn't have east or west here, so we could say below the horizontal would be fine. Or you could say below the positive x-axis. That would be acceptable as well. But your final answer would be, for B, would be 5.81 meters per second at 39.7 degrees below the horizontal. All right, so projectiles launched at an angle aren't really any different than horizontal projectiles. It's the same idea. It's just that in angled projectiles, you have the object going up and then going down. Horizontal projectiles, you have the object being shot straight out and starting to fall. So these are going to go up and down. Horizontal projectiles just have kind of a downward path. What do we know about objects launched vertically, straight up in the air? Well, we know that when they go up in the air, that their acceleration rate is negative 9.81 meters per second squared. We know that the top of the trajectory is their max height. We know at that point they have no velocity. And if we were talking about what their displacement is, we can figure out how far they went up relative to, say, the ground from where they started. But we treat angled projectiles the same way that we treated horizontal projectiles. We break them down into components, x and y, and we can find the overall values. So when you're looking at this picture, the light blue would represent an object traveling, say, up into the air. And we notice that it's getting higher and higher, that the distances between the blue changes. It gets less and less because it's slowing down as it's going up. It reaches max height, and the red represents the object heading back down, and we notice that it's heading back down. We see it's getting more distance covered because it's speeding up. And we also notice that the height values are the same going up as they are going down. The brown down here represents the forward velocity of the projectile, Vx, and we see that they all have the same distance in between each one, so we know that Vx is constant. And then the purple represents an angled projectile. And what can you tell about the angled projectile along the y? Well, notice these heights are the same as the blue and the red. It's behaving exactly the same way as if you just threw it straight up and straight down. And notice the distances forward are the same as the forward distance of the brown down at the bottom. So you have this pattern for every single, well, it's not just angled projectiles, it's horizontal projectiles as well. They behave the same way vertically as an object thrown straight up and straight down. And what can we see as far as the tendencies go for the vector? Well, let's look at this one first. If we launch this object up into the air, what do you notice about each one of these Vx vectors? Are they changing lengths? They're not. That's because, as we said, the forward component, the Vx component, doesn't change. It stays constant. What do you notice about the Vy? Why is it missing up here? Why is there no Vy? Well, again, think of an object being thrown up into the air. As it's being thrown up into the air, it's getting slower and slower and slower. And when it reaches max height, there is no velocity up and down. There's still a forward velocity the whole time. But at the top, at the peak, at max height, there is no velocity along the y-axis. So we don't draw anything. There's nothing there. And then it starts to fall. Again, remember, it's still moving forward the whole time. And what's going to happen as it's falling? Well, we see that the Vy vector gets longer. And why is that? Because it's increasing in velocity as it falls. And notice the changes over here. Look at the length of this. Remember, we're looking at the same height here. This one's on its way up. This one's on its way down. Notice the value or the length of these two vectors, the purple, are the same. And same thing here. This one and that one. Same length, pointing different directions. And then what's the green supposed to represent? Well, the green is supposed to represent the overall velocity, the Vx combined with the Vi. And the only thing missing from here would be the angle. So we say that a projectile follows a certain trajectory. Basically, it's its pathway through the air. And the shape that a projectile makes is called a parabola. So as an object is flying through the air, you're always going to see this consistent shape, and we call that shape a parabolic path. Remember, we ignore air resistance. We don't talk about air resistance when we talk about parabolic paths of projectiles. A horizontal projectile still has a parabolic path, it's just half a parabola. So when we're looking at a vector for an object that's angled, we have the angle here, we have the initial overall velocity. Notice how it's written. It's written as just VI. There's no VI Y, there's no VI X. This is just the overall velocity of the object. So this could be like a football being thrown or a golf ball being hit into the air. Well, we know that object is going forward. We call that VIX. So because this is initial, we would call it VIX. And I know that VIX is the X component. And I know if I was going to solve using trig, if I was going to solve for the VIX, I would take the hypotenuse, VI, and I would multiply it by the cosine of the angle. Why cosine? Well, because cosine is the adjacent side. And if you're having trouble understanding where we rearrange that from, remember cosine is adjacent, which would be VIX, over hypotenuse, which would be VI. So how do I get rid of VI? Multiply both sides by VI. And you see that and that are the same thing. And how about the VIY? What about this right here? Well, that is the initial velocity along the Y direction. So if we're going to talk about the Y, we would call it VIY. So this Y should be right there. VIY equals VI sine of theta. Well, why is it sine? Well, this side is opposite the angle. So if I had sine theta equals opposite, the opposite side would be VIY over the hypotenuse would be VI. How would I solve for VIY? Well, I'd multiply both sides by VI, and I would end up with what you see there, VI sine of theta. So you have to get into the pattern of recognizing that these are the formulas that you just come up with without having to rearrange it multiple steps. You just should know how to get VIX and how to get VIY. And again, the reason there's I there is because this is considered the beginning of the path, the beginning of the trip of the object. So in a angled projectile, when the initial velocity is less than 45 degrees, the forward velocity, the Vx, is going to be greater than the upward velocity. And if you think about it, it makes common sense. If I shoot something, let's just say 36 degrees, that's less than 45. It's going to be moving more forward than it is up when it's initially launched. So we would expect the x component, the Vx, to be a bigger value than the VIY. Again, this I should be right there, like that. If the angle is greater than 45, well, now we have a situation where, let's just say this was 56 degrees. That's definitely greater than 45. Now it's going to be moving up at a higher, faster rate than it's moving forward. So the value for VYI is going to be greater than Vx. And then when it's at 45, well, that means both sides have equal values. So the Vx, whatever it is going to equal the Vyi. Now, of course, remember, this is initially. This is right when it takes off. After it takes off, Vyi starts to change. Of course, Vx is constant, but Vyi is going to stay, or it's going to start to slow down, get smaller and smaller as it's rising and rising. So, at 45, same values. Below 45, Vx is greater than VIY, and greater than 45, VIY is greater than Vx. And we've talked about range already. Remember, range is how far horizontally a projectile goes. So if it was launched up in the air and lands here, this is the range. So how does the range change as you change the angle? Well, it's interesting. Range increases from 0 to 45. As you go up to 45, your range gets greater and greater and greater. At 45, you're going to get your max range. Now remember, this is ignoring air resistance. So no wind, nothing is considered in these patterns. And then the range decreases from 45 up to 90. So from 0 to 45, range goes higher and higher. So it goes farther and farther horizontally. And then from 45 to 90, it decreases up to 90. And of course at 90 it's going straight up and down, so there's no range at all. And then at max range is at 45 degrees. So if they are complementary angles adding up to 90, they're going to have the same range. So if you think about a 60-degree launch and a 30-degree launch, so this is 60 and this is 30. Even though the x component of the 60 degrees, even though it's going to be a lot shorter than the Vx component of the 30 degrees, this one is going to spend more time in the air. The 30 degree doesn't spend as much time in the air, but is moving forward at a faster rate. So what happens is they both end up with the same range. So if I fire a projectile at 30 degrees and I fire a projectile at 60 degrees, even though their angles are different, because they add up to 90, 60 plus 30, I'm going to get the same range from both of them. Again, that's because the one with a higher angle, even though Vx is smaller, Vy is greater. So it's going to spend more time in the air as it's moving forward at a slower Vx. The 30 degrees, even though it's not going as high, along the horizontal, it's moving faster. This means that 25 degrees and 65 degrees are going to have the same range. Again, they add up to 90. This means that 10 degrees and 80 degrees are going to have the same range. Again, they add up to 90. This means that 5 degrees and 85 degrees are going to have the same range because they have a complementary of 90. So interesting ideas with angled projectiles. All right, well, how about the time in flight? Well, if we recall back to free fall, we knew that if you threw something straight up into the air and it came back down and you caught it at the same height, that whatever the time it takes to get up to max height was equal to the time that it takes to get back down to the original starting point. Well, with projectiles, it's no different. When you launch an angled projectile, as long as its starting height and its finishing height are the same, the time to take to max height is equal to the time it takes to get from max height to the ground. But it's very important, and notice this in boldface here, if the starting and stopping heights are equal. If they are not, let's say you are launching from here and it's landing here, then obviously the starting and stopping times are not the same, or the time up is not the same as the time down. But if they are starting at the same point, then it takes, let's say, 4 seconds to get up, and it reaches max height, it's going to take 4 seconds to get back down. Ignoring air resistance, and the heights have to be the same, starting and stopping points. Just like free fall. If we talk about air resistance, if we include it, it's kind of a common sense idea here about how it would affect it. So if you think about a projectile having to travel through a bunch of air molecules, those air molecules are going to impede its progress. So if we include air resistance in our math here, we would see a decrease in the height, max height, we would see a decrease in the range, and we would see a decrease in the time airborne. So the blue here is supposed to represent no air resistance at all. But if we include air resistance, we notice that this red doesn't go as high, doesn't go as far, and certainly wouldn't stay in the air for as long a time. And of course, the mass of the object, the size of it, the speed, all of these affect how strong the air resistance is going to be. A big boulder is going to come in contact with more air than a tiny glass marble, let's say. So there's lots of other things that can affect it. Again, we don't really talk about this a lot, but it is important just to touch on it, that air resistance, if we do include it, does make a difference in the height, the range, and the time. All right, so our angle projectile example, an air rocket is launched with an initial velocity of 10 meters per second and an angle 30 degrees above the ground. What is the range of the rocket? All right, so let's think about this. We have an air rocket. It's going to be shot, and its initial velocity is 10 meters per second, and it's going to be launched 30 degrees above the ground. And they're going to ask us what is the range, and that would be delta x of this rocket, and that's going to be in meters. So think about it. This rocket's going to go up into the air, and it's going to hit the ground, and they're basically asking us what is this distance. Well, I think I mentioned already, when you are trying to figure out a projectile problem, what you want to do is you want to keep track of all of your data with a t-chart. Now, they are asking us to find delta x. We do not know that. We know it's going to be in meters. And there's really nothing else on the x side we know. What about on the y side? Do we know anything on the y side? Well, again, we always know g, 9.81 meters per second squared. Do we know the displacement of the projectile? Do we know delta y? Well, just reading the problem over, you really don't, it doesn't look like we know it, but if you think about it, it says that it's launched above the ground, and it doesn't say anything about it landing above or below where it was launched. So if that's the case, then along the y-axis, the final position and the initial position are equal. So delta y is 0, so we actually do know the displacement along the y-axis. Do we know anything else? Well, right now we do not. But there are some things that we can find out. Whenever you're given an angled projectile problem, after you kind of draw it out and you decide on what you know and what you don't know, one of the things that you can do, especially if you're given the initial velocity, is you can go ahead and you can find your initial components for the projectile. In other words, you can find the initial velocity along the x, and you can find the initial velocity along the y. And all we need to know to do that is a little bit of trig. So let's go ahead and see if we can figure that out. Let's see, Vix is the adjacent side to my 10 meters per second hypotenuse. I know the angle, so to find Vix, I would simply take the hypotenuse times the cosine of 30 degrees. So Vix is 10 meters per second times the cosine of 30. And when I do that, I get Vix of 8.66025404 meters per second. So over here, I can put, I'm just going to write Vx because we know that the forward velocity doesn't change, so I can just write Vx instead of initial x. But that's 8.66025404. So I know a velocity now. Can I find VIY? I sure could. VIY is going to be my hypotenuse. Now again, we're using trig here, so we have to decide on which function to use. VIY is opposite the 30 degrees, so I could use sine of 30. If you're struggling with that, remember that the sine of 30 equals the opposite side, which would be VIY, over the hypotenuse, which is 10. So how am I going to solve for VIY? Multiply both sides by 10. So VIY equals 10 sine 30. And what is 10 sine 30? That is 5 meters per second. So is that something that goes on the y side or the x side? Well, it's the y side, so we can go over here and we can put VIY is 5 meters per second. Now, remember, we talked about angled projectiles that if they are launched and land at the same height, that it takes the same amount of time to get up to max height that it does to go from max height to the ground. Well, another thing is if you launch an object straight up at 5 meters per second and it comes down at the same height, how fast is it going to be going along the y-axis when it just about hits the ground? It's going to be going the same value. So VFY is 5 meters per second, but we have to be smart here because this is a different direction. So I got to make that negative. All right. So if we wanted to find delta x, the last variable we would need on the x side is time. Is there a way to find time on the y side? Can we find time over here? And is it true that if we find time on the y side, that equals the time on the x side? We already have said that in projectile motion, if the time it's moving up and down is the same time it's moving forward, then yeah, the value has to be the same. All right, well look at this. I know 1, 2, 1, 2, 3, 4. I know 4 out of 5 of my variables, so certainly I can find time. And we really have a choice of any formulas from kinematics to solve for this. It probably would be easier to use the one that's least complicated, and that I think would be this one, which doesn't have delta y in it, but we don't need delta y for this formula. VFY equals VIY plus GT. And now I'm going to solve for t, so t would equal, got to subtract the VIY to the other side, and then divide by g. So t equals negative 5 meters per second. Remember that negative sign is there because we added it because it was going the opposite direction on its way down, minus 5 meters per second, that was the initial velocity, divided by negative 9.81 meters per second squared. And we end up with a time of 1.01936799 seconds. So our time up here is 1.01936799 seconds. And again, that's going to be shared over here. Same value, 1.01936799. Again, I'm not rounding. Technically, you're not supposed to round until the very end. Now on the x side, do I know 2 out of 3? Well, I know Vx in red. I know t. We just jumped through a bunch of hoops to find t. Can I find delta x? Sure enough, I can. If I know that the velocity along the x is equal to the change in x, which would be the range, divided by the time, then I can solve for delta x because I know delta x equals Vx times t. And what is Vx? Well, if we go up there in red, we see Vx is 8.6 0.66025404 meters per second. We see time is 1.01936799 seconds. And if we multiply those together, we end up with 8.827985577, and that unit's going to be meters, and then we would round to 3 sig figs. So our answer for delta x is 8.83 meters. And that is the range of this object, 8.83 meters.